We're all looking forward to a future that runs on 100% renewable energy. But what if I told you the biggest hurdle isn't just building more solar panels or wind turbines? Turns out, the real challenge is something invisible, something humming silently inside the grid itself.
Yeah, that's right. The problem isn't about generating enough power on a cloudy day. It's about keeping all of that power perfectly stable every single second. See, as we switch off our old power plants, we're losing this hidden feature that has, well, kept our lights on for the last century.
So let's dive into this silent problem. It's a fascinating challenge that's popped up because renewables are becoming so successful. And honestly, understanding it is the key to unlocking our clean energy future.
So what is this invisible thing we're losing as we upgrade the grid? It really all boils down to one simple concept: inertia.
Okay, so check this out. On the left, you've got the old grid. It was built on these enormous spinning generators. We're talking tons and tons of rotating metal. All that physical mass acts like a giant stabilizing flywheel. It just naturally resists sudden changes. But the new grid, it connects renewables through these little digital boxes called inverters. Now they're super smart and incredibly fast, but they don't have that physical weight. They were designed to just follow the rhythm of the grid, not create it.
And that brings us to grid inertia. It's just the grid's natural stability. Honestly, the best way to think about it is like an orchestra. Those huge old generators, they were like a rock-solid conductor, setting this perfect unwavering tempo. All the other power sources, the musicians, all they had to do was follow along. But now, we're replacing that one big conductor with thousands of smaller digital musicians. So, who's setting the tempo now, right? Without a conductor, you just get noise.
And this is where the story gets really good. We're moving from the problem to a truly brilliant solution. If we're losing our old mechanical conductors, well, we just need to invent new digital ones. So let's meet the technology designed to do exactly that: grid formers.
Okay, I know. That's the official, very technical definition from NERC, the folks whose job it is to keep the grid from falling apart. But don't worry about all the jargon. The key words here are maintain an internal voltage and immediately respond. It's all about taking charge, not just following orders.
Let's break that down into simple terms. A grid-forming inverter, or GFM, doesn't wait around for a signal from the grid, it is the signal. It actively forms a stable voltage and frequency for everyone else to follow. It basically steps up and becomes the new digital conductor for our renewable energy orchestra. It provides that digital inertia the whole system needs to stay in tune.
And here's the perfect comparison. Your standard grid-following inverters are like talented musicians, but they absolutely need a conductor to watch. If the conductor vanishes, they're lost. Grid-forming inverters, on the other hand, they are the conductor. They step up to the podium, set the rhythm, and make sure everyone, from the solar farms to the big battery banks, is playing together in perfect harmony. Now, as you can imagine, designing a digital conductor is, well, it's incredibly complex. It's not just about setting a beat, it's about listening to the entire orchestra and making tiny adjustments in real time. So how are engineers making these things so smart?
Well, there are a few different flavors or strategies for programming these digital conductors. You've got droop control, which is kind of the reliable classic, a straightforward method that's been proven to work. Then there's virtual synchronous machine, or VSM, which is way more sophisticated. It uses some pretty complex math to make the inverter behave exactly like one of those old-school spinning generators. And DVOC is another really clever approach. The main takeaway here is that this is a super active field of innovation. And the tech is getting even more advanced. Researchers are now working on what's called full state feedback. Think of it as giving the conductor a super brain. Instead of just setting the tempo, it's now listening to every single instrument, understanding what's happening across the entire grid, and making intelligent decisions based on the whole picture, all at once. It's amazing stuff.
Okay, so you could have the most brilliant design in the world, but how do you test something that's supposed to prevent a nationwide blackout without risking a nationwide blackout? The answer's pretty cool. You build a virtual world. This incredible technique is called Power Hardware in the Loop, or PHIL, and it's really the best of both worlds. You take the actual physical inverter, the real hardware, and you plug it into a supercomputer that pretends to be the rest of the entire power grid. It's basically a flight simulator for our electricity system, a perfect, safe sandbox where you can throw virtual lightning strikes and massive heat waves at the hardware just to see if it holds up.
And this is what that actually looks like. On the left, that's the real hardware setup at the University of Texas at Austin. That's the physical device. On the right, that's a picture representing the massive virtual grid it's plugged into. So the hardware thinks it's powering an entire city, and the researchers can just sit back and watch how it responds to any crazy scenario they can dream up.
And this is what success looks like. Those smooth lines on the screen mean that when the virtual grid got hit with a major problem, the inverter responded perfectly and kept everything stable. This is how you prove, safely in a lab, that this technology is absolutely ready for the real world.
So proving the tech works is one thing, but getting it deployed everywhere, fast, and affordably, that's the next giant leap. So how do we speed up the process of actually building this future grid? This is where teamwork becomes absolutely essential. The UNIFI Consortium, which is this partnership of top labs and universities, is tackling this problem head-on. And instead of keeping all this amazing tech locked up, they're making it open source. They're basically giving away the blueprints so that anyone can build on it, test it, and make it even better. And the whole process is designed to be super accessible. You can just go to their public website and download everything you need. The hardware designs, the software code, even the shopping list of parts. You can build your own grid-forming inverter, run your own tests, and this is the best part. You can contribute what you learn back to the community, making the design better for literally everyone.
And this isn't just an idea on a whiteboard. What you're looking at right there is the actual hardware. That's the UNIFI open source reference design. That circuit board is a real, tangible building block for the grid of the future, a piece of tech developed by some of the smartest people in the world, and now it's available to innovators everywhere. So yeah, the big shift to renewable energy is creating this silent problem, but the solution is an equally silent, incredibly intelligent one. So maybe the next time you flip a light switch and the power just comes on instantly, you'll think about that invisible intelligence, that silent digital orchestra working behind the scenes to keep our entire world in perfect harmony.